As you know, the transformers are changing the way that we are processing the NLP data. In this video, let's have a high level understanding about the components of the transformer that will help you to get a deeper understanding at a later point. So this is a very high level understanding about transformer, and these are all the building blocks whenever you are starting your learning journey in this natural language processing. So this is a very basic representation of the transformer architecture. Now in the transformer architecture, this has been clearly created for the task of neural machine translation. Now what exactly is this neural machine translation? It's a task where I'll input in my language A and I'll get the output in my language B. That is what a neural machine translation is all about. You can take an example of Google Translate. So when you say Google Translate, you'll you'll input in one language and you'll get the output in another language. That's what the task is, neural machine translation. Now, why is it important? Now, the reason this task is very important, especially in the world of natural language processing, is previously, prior to transformer architecture, we were making use of RNN or LSTM in order to work with these kind of architecture, and we were creating an encoder decoder architecture. Whatever the data that I'll get from the user, I'll process the data through a specific set of layers. We call it as an encoder layers. And this encoded data will be moved to my decoder. So input, encoder, whatever the output that I'll get from the encoder, let's say I'll call it as context. This is the compressed representation of all the input data. And I was using this context as an input for my decoder, and the decoder was generating the output in another language. So this was the encoder decoder architecture before the transformers. And then researchers have come up with the advanced functionalities, and what they have decided is, instead of simply using a single context, why don't we include an attention? That's when the attention came into picture. The research paper, attention is all you need, that's what it talked about. It said how the attention adding to the context will help us in improving the overall accuracy of the model. Now, along with this attention, what had happened in the NLP area was, so the researchers came up with the another technique, that's the transfer learning technique. They came up with the ULM fit, which is a framework or an approach which introduced the transfer learning approach to the natural language processing as well, because at that time the transfer learning was mainly a mainstream in the computer vision. And ULM fit paper told us that the transfer learning can be extended to the natural language data as well. Now with the combination of attention and the transfer learning approaches, this this overall idea or this concept of transformers take took a steep turn. I mean, like this actually gave rise to the it will not be wrong if I say that these two are the key things for the transformers. Now with the concept of attention and the transfer learning, the overall transformer architecture came into picture. Here in my encoder, in this transformer architecture, we also have the encoder decoder architecture. Now what we'll have is, first I'll have an input data, and this input data will be sent to my input embedding, where I'll be generating the compressed representation of my text data with the help of word embeddings. Now the best part in this scenario of transformers is I can send all the input together to ensure that we are specifying in a correct sequence, because that's what the language is all about. We are going to send the data to our positional encoding. The output from this positional encoding will be sent to my multi-head attention. So this will help the model to learn the dependencies from one data to the other terms that I've got in my sequence. And here I'll be using the multi-head, hence we call it as a multi-head attention. At this point, we call it as a self-attention. The reason is I'll be learning the relationship between my current words to the other words in my sequence by itself. That means by looking into the data itself, the sequence itself. Hence it's called as self-attention. And it moves to the add and normalization layer, followed by feed-forward network layer and add and normalize layer. Now coming to the right hand side part, this is my decoder part. In this decoder, here we've got the data. So whatever the data that passes through the decoder, I'll first send it through embedding, which is the compressed vectorized representation of the text data. We are going to add the position details. This gets passed through the multi-head attention, add normalization layer. Then followed by multi-head attention, feed forward layer network, and so on. Here, this attention is called as mask attention, and this is the cross attention. You can clearly see we've got three types of attention: self, mask, and cross attention. So this is the overall architecture of the transformers. We'll get the data, we'll pass through to the input embedding, we'll add the position details, we'll send it through the multi-head attention, which is going to learn the relationship between other words in the sequence, pass through the feed-forward network, and once the encoder stack is complete, we will have the context. And using that context as well as the mask details, I'll have a cross attention layer, and this is the masked attention layer. So once the data passes through encoder decoder architecture, the encoder finally gives me the output in terms of probability, that is with the softmax activation. So this is the overall high level architecture details about the transformer architecture. So team, if you want to learn more, please let me know in the comment section. I'll be happy to take you through the in-depth explanation about the transformer architecture in the further videos. So thank you so much for watching, and I'll see you next time.